We will now talk about the race condition. First, I would like to talk about the race condition and the concurrent program concept, and then we will talk about the defense solutions. Let's use a program example to demonstrate the race condition problem. Assume that there are two methods that run by two different threads. These two methods access the shared integer variable count. Since the two threads attempt to access the same memory, and the execution of the statement belong to the two threads could be out of order and interleaved. The execution of this interleaved statement may lead to different result. This is not the only problem as it appears to be. Each statement in this method can be further represented as multiple assembly code statement. As looks like this. So let's analyze this assembly code statement for the statement count plus 2 and assign back to count. The count variable is increased by 2, and the result is assigned back to the count variable. So the first assembly code statement is note is the reference, the load account, which is reference the count variable. This is actually a very complex process. First, the memory address of the count will be pushed onto address bus, sent to the main memory, locate the memory position in the main memory, retrieve the data values stored on the memory location, and then put the data onto a data bus, and then send it back to CPU, and then stored in one of the register for computation by ALU. Okay, the second statement is add 2. The computation is done by CPU, the ALU unit, and the result will be saved into the output register and then store it on the register that previously stored the value of the count variable. Okay, the third statement is the store count. This will store whatever on the register back to the main memory at the memory location pointed by the address of the count variable. This is also a very complex process. Two buses, an address bus and a data bus are needed. The data bus stores the value previously stored on the register, and the memory bus stores the memory address stored in the memory register for the count variable. Whenever these two buses arrive at the main memory, the memory management unit will locate the exact main memory position and then store whatever on the data bus to that memory location. After that, the bus will come back to CPU. As you can see, the assembly code statements are not atomic and can thus be interleaved, which may lead to different results or unexpected results as shown here. Now we will show through an example, by using a program example. So the present class with the compute method, and with the global count variable, shared count variable, and the implement runnable theme will call the present object and call the compute method. And this is the main. So it has a demo theme method, which will build 2 threads with the shared present object. And it will repeat for 100 times. Let's run. And as you can see, the result could be unexpected, could be A, B is 9, A is 9, B is 9, or A is 9, B is 7. And they even have like 12 or 9. Okay, let's demonstrate this race condition problem by one more time. Okay. Look at this one single statement. Count pass. For the global variable count. Again, this single statement will be represented by 3 assembly code statements similar to the process we just discussed above. The first step is load process to load the count variable from memory to register. The second step is the computation of the variable. The third step is the store process, which will store whatever on the register back to the main memory location the count variable pointed to. As you can see, we could have different results based on different running process sequence. Okay, so that's pretty much about the race condition theory.